So here we have lesson 12, which is all going to be about drug detection. So let's first talk about steroids. Steroids are lipids with a structure consisting of four fused rings, known as a steroidal backbone. An example of a steroid is cholesterol, which has the following structure. Okay, so you can see the four fused rings. They're colored in our image there. Okay, you can see how big and complex the structure of a steroid actually is. So steroids are found in some hormones, especially in the sex hormones. Male steroid hormones are collectively called androgens, of which testosterone is the most important. These hormones are known as anabolic steroids due to their role in promoting tissue growth, especially of muscles. They have been used as performance enhancing drugs by athletes in sports such as weightlifting and cycling, as they can increase strength and endurance. Anabolic steroids are usually synthesized from testosterone and include drugs such as nandrolone, stanozolol, and furosemide. So, as you can see, with the use of these steroids as performance enhancing drugs, it is important that scientists can detect these drugs within an athlete's body. So, the most common method for detection of steroids in blood and urine samples is known as gas chromatography mass spectrometry, or GCMS for short. This uses the two techniques of chromatography and mass spectrometry combined in sequence. So, the gas chromatography is used to separate the chemical mixture into pure chemicals, and mass spectroscopy identifies and quantifies the components. Okay, so this GCMS is used to detect what kind of steroid and how much of the steroid is in a person's blood or urine sample. So let's start first with the gas chromatography. Different components of a mixture have different affinities for two phases, a stationary phase and a mobile phase, and so are separated as the mobile phase moves through the stationary phase. In gas chromatography specifically, these phases are seen as a stationary phase in which a microscopic layer of a non volatile liquid is coated on the walls of an inert solid support. And then we have the mobile phase, which is usually made up of an inert carrier gas such as helium. Separation of the components of a mixture is determined by the different rates at which they move through the instrument. These rates differ according to the boiling points and solubilities of each component, as these determine the relative associations of the molecules with the liquid, which is stationary, and the gas, which is the mobile phases. Okay, so boiling point solubilities play a very big role in determining how quickly these components will move. So, really quickly, I just want to go in through how it works. I'm going to show you a picture on the next slide. The gas is mixed with the inert carrier gas and passed into the column. The temperature in the column is controlled and is typically lower than the initial temperature so that some components of the mixture condense and may dissolve in the liquid phase on the walls of the column. Depending on how they partition themselves between the liquid and gas phases, each component of the mixture will be eluted at a specific interval of time known as its retention time. Changing the temperature of the column controls the retention times and therefore the amount of separation of the components achieved. A detector is used to record the passage of each compound as a peak and the area under the peak is a measure of its concentration relative to a known standard. Okay, so here we can see the picture of our gas chromatography, where you have your gas such as helium at the beginning. You have your syringe containing your sample, which is injected into the machine. Okay, it's inside the temperature controlled oven, and you have a column which is coated with that stationary phase, that liquid. Okay, and then it goes through the columns, and once it's on the outside, you have a detector and a recorder to look at the different components. So once it goes through the gas chromatography machine, as we can see on our picture all the way to the left, some of the sample is then passed directly to the mass spectrometer for identification. So this avoids the need to identify compounds from their retention time. So it's used in combination, the gas chromatography and the mass spectrometry, to get a readout of the sample that was injected at the beginning. So here is an example of what we might see in this process. So the figure shows the spectra of a drug known as nandrolone. The upper diagram shows the gas chromatogram, and the lower diagram shows the mass spectrum, which clearly shows the molecular fragment. So you could see that in the top picture you have that peak that can be used as a tool in identification. And then you can combine that with the mass spectra, which we have learned about previously, to identify which kind of drug you are looking at. Another common drug that needs to be detected is alcohol. So how does that work? Well, ethanol acts as a depressant, which means it decreases the activity of the central nervous system, which causes short-term changes in behavior and long-term dependency. A person whose judgment is changed by the presence of ethanol in the blood is said to be impaired, which is potentially a dangerous condition. Again, definitely a dangerous condition if you were to be driving or something like that. So most countries regulate how much alcohol you can intake before driving or operating equipment. So there has to be a test that have been developed to analyze the alcohol consumption. And these tests usually measure the BAC, or the blood alcohol concentration, as a mass per volume, which is usually milligrams of ethanol per cubic centimeter of blood. Ethanol is a volatile compound, and so establishes equilibrium in the lungs between the solution in the blood and gas, which is released in exhaled breath. So when we intake an alcoholic drink, that ethanol is dissolved, so it's aqueous, and it establishes this equilibrium, which we can see in the equation, with the alcohol that is the vapor when we exhale it. So the equilibrium constant for this reaction has a fixed value at a particular temperature, so measurement of ethanol in the breath can be used to assess the blood alcohol concentration. Instruments that measure ethanol concentration in a sample of breath and convert it into blood alcohol concentration are known as breathalyzers. So this is what we're going to get into. We're going to look at how do breathalyzers work. Roadside breathalyzers use redox chemistry to measure the ethanol concentration. Ethanol is oxidized to ethanal and ethanoic acid by the oxidizing agent potassium dichromate. We've seen that before. During the reaction, the chromate is reduced to chromate 3, which causes a color change from orange to green. So we can see that as our redox reaction, the color change, which is an indication of a different chemical, ethanol being converted into ethanoic acid. So the extent of the color change can be measured using a photocell and so be used to determine the ethanol concentration. The test is often used as a preliminary test, which may lead to further, more accurate tests using intoximeters. So a breathalyzer is first used by police if you get pulled over, but then those samples can be sent to the lab using more accurate tests. An instrument known as an alkosensor uses the electrochemical processes in a fuel cell to measure ethanol concentration. The fuel cell contains 2 platinum electrodes with a porous acid electrolyte between. Exhaled air is passed over the cell, and any ethanol present is oxidized to ethanoic acid at the anode. Okay, so we're going to take a look at this redox chemistry that is actually occurring in this alkosensor. So here we have a series of equations where we have the ethanol being converted into ethanoic acid. So protons and electrons released from this reaction pass to the cathode where they reduce oxygen to water, okay, which we can see in that middle equation. The overall reaction is the oxidation of ethanol to ethanoic acid and water. So the electric current produced by the reaction is measured by a computer and used to calculate the BAC. Fuel cell intoximeters are accurate and portable and are widely used. Okay, so for the alkosensor, there's a reaction at the anode, there's a reaction at the cathode, and you get the overall reaction for the oxidation of ethanol to ethanoic acid. The last thing we're going to talk about is the structure of many organic molecules can be determined using a combination of infrared spectroscopy, mass spectrometry, and proton NMR. So much of this will be a review, but first we have mass spectrometry, which is used to confirm the presence of a compound through the peak of the parent molecular ion. So we talked about how the largest peak on the mass spectrum usually corresponds to the total mass of the structure. So here we're comparing salicylic acid to aspirin. You can see they have different mass to charge ratios, and therefore they can be identified using a mass spectrometer. Right, we can see that here we compare the mass spectra of both of our compounds, and clearly they are different. We also talked quite a bit about infrared spectroscopy, IR, and functional groups in compounds show as characteristic absorption peaks in infrared spectroscopy. So this would be looking for things like the ketone or aldehydes or hydroxyl groups. We also talked quite a bit about proton NMR. It's the technique that enables chemists to Identify a sample through its chemical shifts, the number of peaks, as well as looking at the area under the curve and the splitting patterns. So again, if we have a sample that we look at through proton NMR, we can look at the protons to figure out where they're located in a compound, how many protons we have, and then finally we look at the splitting pattern, which is based on nearby protons. All right, why don't we do 2 wrap-up questions where we look at these tests used to identify compounds. So, in number 28, infrared spectroscopy can be used to detect ethanol in breath samples. Letter A says use the structure of ethanol to identify peaks on this spectrum. Okay, well, one of them is already labeled for you. The other one is the large, very broad peak around 3200. Okay, so we have the CH bond, which is already labeled, and then we have the around 3200 to 3600, more specifically is characteristic of that hydroxyl or the OH bond. Letter B says state which of these peaks can be used to distinguish ethanol from water vapor in the breath. Okay, so which one of these 2 peaks would be better at distinguishing ethanol from water vapor? Well, we just have to look which one of these is in ethanol and which one of them is not in water, and that would be the peak at 2800 to 3100. That is the CH bond. There is no CH bond in water. Finally, letter C, people who suffer from diabetes often exhale propanone vapor in their breath. Suggest why they may therefore give a false positive result in the infrared spectroscopy test for ethanol. Okay, well, we know propanone, if you can identify the functional group, the known ending should tell you that it is a ketone. So that does not interfere with the ethanol. But what propanone does have is the C to H bonds, which would maybe give a false positive as belonging to ethanol rather than the propanone. All right, we have one more problem here. We're going to look at 29, which is going to start by looking at caffeine, and we're given the structure of caffeine. In letter A, it says, in the mass spectrum given, which peak supplies the strongest evidence for the presence of caffeine? Well, we talked about this quite a bit. It was mentioned earlier that the molecular ion at the end, which is the around 194. Okay, that gives the total molecular mass of our structure of caffeine. Letter B. Identify 2 characteristic absorptions in the infrared spectrum that are consistent with the structure of caffeine. Okay, so there are a couple that you could include, which include the C to H, for example, in methyl groups. The other one is the C to double bonded to an O. That would be around 1700 to 1750. Letter C talks about how many peaks would you expect in the proton NMR spectrum of caffeine. What would be their relative areas and splitting patterns? Okay, well, if you go back to the structure of caffeine, you should try and figure out how many protons are possible. And if you look, there are 4 different protons, which would give us 4 different peaks. And their relative areas are 3 to 3 to 3 to 1, because we have 3 methyl groups. And there is 1 proton that is not drawn, but it is still present. And in all of these cases, they would all be singlets. Finally, letter D, name 3 functional groups present in caffeine. So if you take again, look at the structure, hopefully you remember your functional groups, but we have amines, we have amides, and we have an alkene.